Hello, my name is Drew Mills, and this is my video report for Lab 4 Oscillations. The objective of this lab is to analyze the motion of a mass attached to a spring as it oscillates in an arc. We will use Tracker to observe real-world data and GlowScript to create a computational model, allowing us to evaluate the conservation of energy and the predictive power of the momentum principle. The analysis is grounded in two major physics concepts. First, Newton's second law, also known as the momentum principle, which says that net force is an objective resulting in a change of momentum over time. This allows us to iteratively predict velocity and position. Second, the energy principle, whereas change in energy of the system is equal to work of the surroundings. Since our system, the mass, the spring, and the earth is closed, the total work done by the surroundings is zero, meaning change in energy should be zero throughout the motion. Using Tracker, I analyzed the provided video. I calculated the mass to be 0.402 kilograms and the calibration length to be 0.7 meters at rest. I set the origin at the attachment point, resulting in initial position of negative 0.107 as the x, and negative 0.632 as the y in meters. The mass starts from rest, so the initial velocity is a zero vector. I tracked the center of mass for approximately 9.3 seconds to capture several full periods of oscillation. In GlowScript, I initialized the mass and position to match my tracker observation. To calibrate the model, I calculated the spring constant, K sub s, by measuring the time of three oscillations, in the y direction, yielding in a period t of 1.52 seconds. Using the formula, or the derived formula, t equals 2 pi root mass divided by k constant, I found the spring constant to be 6.872 Newton meters. I then solved for the relaxed length using the static equilibrium position, finding it to be 0.126 meters. The code calculates the vector L by subtracting the spring's position from the ball's position. Then we find L hat and S, the magnitude of the stretch or compression for the energy principle I defined. Using the equations of kinetic energy being 1/2 mv squared, gravitational potential energy as mgy since it's close to Earth, and the spring potential U sub s being 1/2 spring constant times s squared. Total energy is the sum of all these three. Inside the calculation loop, I first calculate the force of gravity and the spring force using Hooke's law. Summing these gives us F net, obviously. Then I update the ball's position and velocity using the iterative formulas derived from the momentum principle. Finally, I update the length of the spring and calculate the change in energy, delta kinetic energy and delta potential of gravity, and delta potential of spring to ensure the energy principle is tracked correctly. When comparing the models, the period of oscillation aligns very well, particularly in the y direction. However, there are slight discrepancies in the x direction amplitude over time. This could be due to possible error 1, forces like air resistance or initial spring friction that the model ignores, and possible error 2, human error and tracker, such slight misplacements of the center of mass during fast-moving frames. So what does it mean? Is the energy principle satisfied? Yes. As shown in the graph, the change in total energy, the orange line, remains at zero throughout the entire simulation, while K, U of G, and U of S fluctuate. Their sum is constant, confirming that energy is conserved, as 1.614 seconds in the Y data as 1.519 seconds. The difference exists because X period is more dependent on the length of the pendulum, while the Y period is strictly governed by the spring stiffness and mass. In conclusion, overall, the computational model provides a highly accurate prediction of the experimental motion, and the energy analysis confirmed the fundamental laws of mechanics. Thank you for your time.